So lecture number 3, major theory. So today we'll discuss on Borel sigma algebra. A Borel set. The elements of Borel sigma algebra is called Borel set. So what is Borel set? So we see that we need a sigma algebra script F because all the subset of a uncountable or maybe for R real number is a very tough, very complicated set. All the subsets are some subsets are very complicated. So we just take only a special type of sets. Actually, the all type of known subset we are taking care, and we take a sigma algebra because we need these three conditions, that at least this whole set omega in this collection, and if A is there, then A complement must be there, and if there A1, A2, AN is a countably many set, a sequence of set, then their union in this sigma algebra, their union must be in the sigma algebra. So we know what do you mean by this countable union. So hence all the intersection also there. So now, what is the smallest sigma algebra? The smallest sigma algebra is this. You just take only these two, this and phi. So once you take omega, the whole set, you have to take the phi also, as the complement is there. Now, what will the slightly larger than that? So, okay, take a subset of omega, which is not phi, say is not phi, and A is not also omega. So take other set. So this is my whole omega, and this is a set A. Now, if you want to take A as the element of the sigma algebra, say sigma algebra is named, say, script F1, then we have to take omega, we have to take phi also. If I want to take A, we have to take A complement also. So this A set and then A complement. So there are four sets: A complement, omega, and phi. This is a sigma algebra. If you take any two set of them, they are in complement, their union is also in. Now it is no question of countable union. It is a finite number collection, so you have finite union. So every finite union is belongs to this sigma algebra. Now how do we can construct that? We construct like that. So if you take A and A complement, now we have to take the union of these two. So you can take their union. So this union is this is called sort of atomic structure. The A is the atom, and if you take A complement and their union, A complement, which is actually omega, whole universal set. And if you don't take anyone, then it is actually phi set. So four set are there. Now take slightly larger set. Say this is A and this is B. This is omega. So if you want to say this is script 2 F2, you have to take omega, you have to take phi also. Now if you want to take A and B both, say A and B is, say, non-empty, not disjoint, and also A is not a subset of B and B is not a subset of A. Assume these three. So there is a AB are distinct, AB are and also AB A not equal to B. AB are disjoint and they have a common intersection part, and they have some element which is not in A, in B, or not in B and in A. So then what is a sigma algebra? Now sigma algebra should contain the union of all these things and complement also. So you have to take the complement part, A complement, B complement. Then you have to take the union. So what you have to take union? So A union B. Other is A union B complement, and another is A complement union B, and other is A complement union B complement. Now question, is this a sigma algebra? We have a 10 subset, but it is not a sigma algebra, still not a sigma algebra, because A union B complement is not there. So you have to take A union B complement also. Now question whether this complement is there or not. No, the complement is not there. So A union B whole complement and their complement is not there. So we have to take that. So you have to take this complement also and this. Now that is actually A intersection B. So is this a sigma algebra? No, still it is not a sigma algebra. Why? Now, so this type of construction is slightly complicated. So how do you know the sigma algebra is? So you have to take complement, then take the union, again their complement, again their union. The two things is there. How do you know that we exhaust all these things? And how do you know that we are not repeating? Maybe such a way that we are taking complement union. Maybe same set will be occur more than one times. So idea is this: you have to just take this portion, this A minus B, which is actually A intersection B complement, and B minus A, this set, because this you can't further decompose this thing. So this is called atom or atomic set, and this part A intersection B, and the other rest A union B whole complement. So this fourth portion, this fourth thing, is actually a partition of the whole omega. It creates a partition, and this is an atomic partition. So you can't further decompose this using AB. Now what are the set in sigma algebra? Now you can easily write all the sets of the sigma algebra containing this four. How? Idea is this: you have a say phi, okay, and then just take all these things one at a time. Just B A complement intersection, then A intersection B, and then A union B whole complement. So you can write this as it's in a better form. You write in this form that it is A complement intersection B complement. So in the intersection form, so either is a complement A or A complement, or B complement, and their intersection. These are the atoms. Phi is not the atom. These four are atoms. So you take just one atomic set, then phi. Now take two atomic set. If you take this two, this portion and this portion, you will get A. A is actually consider two atoms. Now this and this is actually B complement. Now this and this actually A delta B. There is one more set is not here, A delta B. You know what is A delta? A delta B? What is A delta B? A delta B is just symmetric difference. A minus B union B minus. This portion, and this portion. So these two atomic setting. So we have this. Then we take this and this. So B, we take this and this. It is just A minus B whole complement. So it is A minus B. So A intersection B complement their complement. So this portion is this and this. No, sorry. This portion is this is union of three. So we have this union one, this and this, this and this. We have the union of this and this. Now 1, 2, 3. We have 3 many. We have 6. It is 4C2. Since there are 4 atoms, we take 2 at a time. So 4C2. We already have 3. And next this 1 B. This is B. This is right. This is actually yes. This is A delta B complement. A delta B complement. The last one is A complement. So we have 6 many subsets taking 2 atom at a time. Now 3 atom at a time. 3 atom at a time is just A intersection B complement, then whole complement. B intersection or A complement intersection B, then whole complement, and then A intersection B whole complement, 3 at a time, and then A union B, 3 at a time, and the 4 at a time is this. So there are 16 many subsets. There are 16 many subsets in the sigma algebra. Now there is no other subset in the sigma algebra. So if you construct in the previous way, you actually miss something. So we miss some this and A symmetric difference B complement. We miss these two sets, and you can check that these sets are somewhere in this here. So A intersection B complement is actually A complement union B. You can check match one with other. So this form is sometimes called DNF form or maybe CNF form. Conjunctive normal form or disjunctive normal form. If you write some set in the union of some intersection of the set, it is a one procedure, and another procedure, writing a set in the form of intersection of the union. So take an union first, then take the intersection. But this is method better. If you take intersection first, then take the union. So the intersection means you have this atomic structure, atomic set, and then you take their union. So union should be there. Now, if say if A is a subset of B, whatever. If A is a subset of B, then this is A, and this is B. So this is B minus A, and this is B complement. Actually, you have 3 atom now. Now, if you have 3 atom in sigma algebra, you will get 8 many sets. So if you don't take anyone, so 5. Start with 5. Take one at a time. The atoms A, B minus A, and B complement. Then take 2 at a time. So 2 at a time is B, and then A union B complement, and then A complement. And take now 3 at a time. So the whole amount. Again, if A and B are such a way that A and B are disjoint, then you take you will get 8 many subset. In the same way, phi, then A, then B, then A union B complement. This portion, this are atom, then A complement, then B complement, then A intersection B is phi, then A union B, and then the whole omega. So there are 8. So it is clear that if you have a finite number of set, so if for more general, if you have a finitely many sets, A1, A2, they are disjoint or distinct, and not disjoint, they are distinct. Then it so happen that the number of atom may be then number of atomic set is maximum is 2 to the power n. The maximum possibility, maybe less than that possibility. Like if the two set A and B, the maximum possibility is 4, but it may be 3. So maximum number of atomic set is 2 to the power n. Now, if the atomic set 2 to the power n, then the number of set in the sigma algebra containing this A1, A2, A1, A2, AN, containing these sets containing this A1, A2, AN is 2 to the power n. Now 2 to the power n. So it's the huge. Why it is 2 to the power n? Because if A1, A2, n sets are there, you can choose complement there and then intersection. So you can take A1 intersection A2 intersection AN, or A1 intersection A2 AN minus 1, then AN complement, like that. So 2 to the power n many atomic set and their union. So in union you can take one set, or you may or may not take one set. So there are 2 choices of every time there are 2 choices. There are 2 to the power n many atomic sets, so 2 to the power n many subset in the sigma algebra. If you this is the smallest sigma algebra actually. This is the smallest sigma algebra. This is called the smallest sigma algebra containing A1, A2, A. This is the smallest sigma algebra, A1, A2, A. One can always take the whole power set. If I say I will take the whole power set, then is a obviously sigma algebra containing A1, A2, A. But we are interested what is the smallest sigma algebra. What is the minimum set we have to taken care? That is the smallest sigma algebra. So if you have n distinct set, the smallest sigma algebra containing 2 to the power n many subset maximum possibility. So it is a maximum possibility. But number of atomic set may be less if number of atomic set is just m, which may or may not be equal to 2 to the power n, is less than 2 to the power n, less than or equal to 2 to the power n. Then what is the element number of element? Then number of element in sigma algebra, in the smallest sigma algebra, is 2 to the power n. That is always true. So if you have m many atomic set, then 2 to the power m many set you can construct for that, taking union. So it may be if you have at least n must atomic set is number of atomic sets is at least n plus 1, and maximum it can be 2 to the power n. If all are disjoint, say if all the sets are disjoint, then there are n plus 1 many atomic set. So the collection is huge. Now, for it is finite case, but if it is infinite, say consider say omega as a real number. Now this you can't construct sigma algebra like that because there are infinitely many sets, and if you have infinitely many sets, the construction of these atoms and then construction of the union there is complicated. You can't write like that. You can't say this is 2 to the power n. For it's finite, you can do this. So what is the way to construct a sigma algebra on R? As at least is a fair number of set we have to will take a fair number of set, not just a trivial power sigma algebra like it is a trivial sigma algebra is this. You take just phi and R whole set, and obviously the maximum possibility is this. You just take the power set of R. But we say that power set of R is complicated, and we can't define a measure on that. That's why we have to take a sigma algebra which is a good amount of set in there, but not the whole power set. Now, what set you have to we want to at least which sets we need in our sigma algebra? Say all open set. Say take all the open set in R. If you take all open set in R, you take this collection as say O. This O is the set of all open set. All open set. But actually, no need of take the all open set. Why? We know if you take this collection, say set of all open intervals in R, collect all these open intervals in R, you have this collection, say this is C, this collection is C, and if you have a smallest sigma algebra, sometimes write smallest sigma algebra like that. So smallest sigma algebra containing this C, this collection, sometimes write in this notation. This sigma algebra containing this C. Smallest, this is the smallest. You have to take this open intervals. Now it is, you can easily check that this is actually smallest sigma algebra containing all this open set. One set is easy because this is a subset of the set of because the open intervals are open set. But the all open set can be written as a union of open interval, and that is a Lindenberg-Kovalin theorem. You know this since a real number is dense, there is a dense subset in real number. It is a separable topological space. Since it's a separable topological space, this is a dense subset. Q is a dense in R. Since Q is dense in R, every open set in R can be written as a union of open interval. And if it is a, if it is a compact set, then by Heine-Borel theorem, you can have a finite number of that covering. This Lindeberg covering theorem, and for compact set, there is a Heine-Borel theorem. There are finitely many, but for any open set, there you can have a countably many set which can cover this. Now, if you cover by the open intervals, then there is a countable in many elements of that which cover this. So you can always write an open set in the union of open intervals in R. So if you have all the open intervals are, then open sets are always in there, because we are taking the smallest sigma algebra. And sigma algebra means if you have some sequence of open intervals, that union must be there. So that's why these two are equal. So we can take only just this thing, or maybe we can have this set, say this collection, say half open, half closed. We take this collection, say. And this collection, this is not an open set. This collection is not a subset of this big O set of all open set in R. This collection, but still this collection, the smallest sigma algebra containing this is same as smallest sigma algebra containing this open intervals. That you can prove. How do you prove that? So take a set here. So take a set which is half open, half closed, and that can be written as union of open interval. How? It is easy. It's just n equal to 1 to infinity. A to a minus 1 by n. Sorry. It is, how to write this? B, no, you can't take as a union. Yeah. Is B? No. No, we can't take. We first show that. Okay, we can take intersection basically, because intersection is also there. In the sigma algebra, intersection is also there. So we can take intersection. So this intersection. So this is actually, these two sets are equal. That is trivial to check. That this intersection is actually the half open, half closed. So and we know if the open sets are in there and sequence of open sets in there, then that intersection is also in there in the sigma algebra. That means this type of half open, half closed intervals are in the sigma algebra here. So this type of set is actually in the collection of this. So these are in the collection of this. Now, therefore, that implies a sigma algebra containing all such set is a subset of this. Now, once you have a sigma algebra, this, and if you want to take the sigma algebra, the smallest sigma algebra containing that sigma algebra, it's just equal to that sigma algebra. So if you have a sigma algebra F, script F is a sigma algebra. Now, if you want to take the smallest sigma algebra, which is the smallest sigma algebra containing all the sets of this script F, that's actually a script F. This is the smallest. And if you have a and B, two subset or two sets, then the smallest sigma algebra containing this, sorry, not A, it is a script A, the collection of set. The collection of set is a sub collection of some other sub collection. Then this sub collection sigma algebra containing this small sigma algebra containing this sub collection is subset of this smallest sigma algebra containing this sub collection. So that means from this we get so we have D is a subset of this. So we have this. So D is a subset of this collection, and therefore the sigma algebra of D is a subset of the sigma algebra containing this. But sigma algebra containing this is same as sigma algebra containing C. Now, to show the reverse way, we have to show just C is a subset of sigma algebra containing D, and then from that we can easily show that by similar way the subset of sigma algebra containing D. Now, how do you show this? So to show this, we have to show that every open set is in here. So we have to show every open interval here. Now, how to show every open interval is there? That means you have to show the open intervals can be written as a union or intersection or maybe in complement of the half open, half closed interval, and that can do easily using union. How? So A B open interval is nothing but union over 1 to infinity A to B minus 1 by n closed interval. And this union is actually this open interval. This is easy to verify. So that's why we can, if you start with this all open set, if you start with the all open interval, or half open, half closed, or maybe the left open, left closed, right open, or maybe the both closed. If you start with the both closed, then also we'll ultimately reach to the same sigma algebra, and this sigma algebra is known as this sigma algebra. Set of all such is known as Borel sigma algebra. And any set in Borel sigma algebra is known as Borel set. Now, what are the Borel sets? So we already have a large collection. So all the open intervals are Borel sets. All the half open, half closed, these are all Borel set. These are all Borel, and these sets are also Borel. The all intervals is actually Borel set. And you know this minus infinity, which is actually the set of real numbers, is also Borel set. And any open set is also Borel, or any open set, any closed set, because closed sets are the complement of the open set. Closed set, and all such a sort of open set, closed set, and eventually a singleton set is also Borel. Why? How can we write a singleton set in terms of this half open, half closed? Easy. It is just, if you take one to just singleton B, it is nothing but the intersection of all set. What it is intersection? Yes, n equal to 1 to infinity, and intersection of B minus 1 by n and B closed. So these two set are equal. It's trivial to check, verify that these two set are equal. So all singletons are there. Since all singletons are there, they're countable of singleton set. So union means a countable set. So countable sets are there. So all countable set. Any countable set. Countable set is a Borel set. Like Q, all rationals or irrationals. The complement is irrational. This stuff, all Cantor-like set and other sets is there. Now we know the union of closed sets may not be closed set, but in Borel sigma algebra, union of the all closed set must be there, and that type of set is called F sigma set. Union of closed set or G delta set. So all G delta sets are the union of closed intervals. It's called G delta set. G delta set is a huge collection. All the open sets are in there. All the closed sets are in there. It's a union of closed intervals, closed sets, and all the intersection of the open sets that may or may not be open, or may not be closed. That is called F sigma set. So X sigma set is a huge collection. It's all open sets is there. All sort of these sets are there. All closed sets are there. G delta is also a huge collection. But F delta, F sigma, F G delta is different collection. And now if you take a G delta set, and if I take the union of that, then it is not a G delta set. There is a huge collection. It's called G delta sigma set. So such a way you can have a. There are several Borel sets are there. Which is very complicated also there. It's a huge collection. And whatever set we discuss in real analysis or in probability or anywhere, these are all Borel sets. Finding a non-Borel set is really tough. but there are several many. Is actually more than non-Borel set is huge. In cardinality, more the non-Borel set has a more cardinal number than Borel collection of Borel sets. Basically, the number of Borel set is countable, and number of non-Borel set is number of Borel sets are is the first uncountable LF1, but number of non-Borel sets are LF2, more cardinal number. So we just need this type of set only. Basically, no need of this so complicated set. We need this type of set only. These are the very important collection. Why this collection is very important? This is the question. Why this collection is very important in R? Now, since R is if you take R2 or Rn or any topological space, and if you have you know the in topological space there are concept of open set. In R2 also there are open set. In R3 also there are open set. Now, this you can have a talk. You can talk Borel sigma algebra on R2 or Borel sigma algebra on Rn or Borel sigma algebra on any topological space, arbitrary topological space. It may be collection of any other set, any abstract set. So why this is important? Because we actually find the measure of this set. Now, if you want to find the length, say if we want to find length of a set. So by the way, one thing is important. We write a less than b, but if I say 2 comma 2 close open, that is actually phi set. If I write 2 comma 1, this is also phi set. So if a is greater than b, then it is a phi set. Now if write this close to and then close to is actually set only 2, and if I say close to and this here it is say 1, then it is a phi set again. 2 to 1 is a phi set. So a less than b must be there. So what is the length? This natural thing is it's just b minus a. Natural. So if you have a real line and if you have a 0 here say and 1 here, and if you want to find the length of this part is actually 1. Similarly, say is 2 here and say here is say 5, and if you want to find the length, what is the length of this set? Length of this 2 to 5. It is 5 minus 2 is 3. It's obvious way, is natural way to take the length of a interval in R. That's why you want to take this set in our collection. And once we take this set in our collection, we have to take all this closed, all this open sigma, G delta, F sigma, all the countable, all the finite, all such of this, all sets are in our sigma. All known sets are in our sigma. Once we take this, only this collection, this intervals, and you have to take this interval because we obviously want to. Anyone can ask what is the length of the set which is from 5 to 10, and obvious answer is 5. And once you take this intervals, half open, half closed, all the Borel sigma algebra is in. And that's it. In probability also we discuss on, we do the same thing, because we for a random variable we ask what is the probability of a random variable in between some a to b. That is a natural question to ask, a less than b, which is actually we write in this form. This was so it is a natural question. So what is the probability? We sometimes write this is a probability measure. Say probability measure is say mu is the probability measure, and this probability measure of this mu x say, because it is a random variable is x is there. So what is the probability measure of this set? This is nothing but fb minus fa, where f is the distribution function. Since f is a distribution function, the probability is this. So one can ask that what is the probability measure of this type of half open half closed set. And once you say it is just fb minus fa, and we need a sigma algebra to define this. Now we need this probability measure on the sigma algebra, and the smallest sigma algebra where this half open half closed are there, that is the Borel sigma algebra. So this is the probability measure on this Borel sigma algebra. So what is measure? Measure is this is sigma algebra, and any measure on a sigma algebra is again has like probability. What are the definition? What is the definition of probability? So if there's a probability, and if it's a sigma algebra, and what is the definition of the probability function? This probability function definition is just this sigma algebra is on sigma algebra on this omega. Omega is a whole set which is called the sample space, and this descriptive sigma algebra is called the event space. Now we need this, number one. Number two, if you have a a1 dot 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 a2 dot 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 infinite collection in sigma algebra where these are disjoint, each all pair are disjoint for all I not equal to j, this is phi, then what happens? Then the probability of the union I equal to 1 to infinity, it is just equal to the sum over this. This is the definition in the probability definition. This is the definition of probability. So once this a1 a2 dot 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 the sequence in the sigma algebra, their union is also in the sigma algebra. So we have to find the probability. Once a1 a2 dot 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 this sequence is event, all the elements of the sequence are event, that union must be an event. And anyone can ask you that what is the probability of that event, and this is the sum of the all individual probability because it is disjoint. Now this is a measure. This is also a measure. It's called probability measure. But in more general, what is a measure? This measures is like that. It is just a probability measure, and any general measure is measure on this script tape. Is just a mu is a measure on script tape. This is not in 0 1. It is now 0 to is actually we take the extended real number system. We take one symbol like infinity. Infinity, remember, infinity is not a real number. It is like a symbol. It's a real number union infinity because in general measure the length may be infinite. So length of whole real line is infinite, but it can't be negative. It's a non-negative, such that this first condition is just avoided. The whole set may not be 1. It may be 5. It may be infinity. So if a1 to a in the script f and this the disjoint for all I not equal to j, then the measure of the union is, since they are disjoint, the measure of the union is the sum. Now there is a very important question, whether this sum converge or not. Whether this sum converge. Now these are all positive non-negative terms, and we know it's a series actually, and we know that if all the non-negative term, the series of non-negative term, this if it is a finite, then it is converge, or it may be infinite. So it may be infinite, it is diverge, it can be oscillate. And here for the probability case, it is easier than that general measure because in probability all are finite, all are greater than or equal to 0, and this sum is actually less than or equal to 1, so it is bounded. So since the finite is called finite measure, this type of system is called finite measure. If the whole set as a measure is finite, this is called finite measure. Probability measure is a finite measure. So it is a finite measure. So and the whole measure is 1, the whole probability is 1. And we know if there are non-negative the series of a non-negative term which is bounded, that must converge. So the right hand side is exist because it is a question because whether the sum of the series exists or not. So it's a question of convergency in the series. But since it is a probability, we can do this. Now one more important question, whether can we rearrange the term? That is a very interesting and important question in real analysis, that whether can we rearrange, say if this is a series a1 a2 dot 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 dot, this is a series, and if we want to rearrange the term, say a2 plus a1 plus a4, something like that, we just slightly rearrange the term, first even then the odd term. Is these two series equal? The answer is no, may or may not be equal. The sum, this s1 s2 may or may not be equal. May or may not be equal. These two may, s1 or s2 may not be. Maybe so happen that s1 is converged but s2 is not converged. Maybe so happen s2 exists but s1 is not exist. It may so happen that both is not exist. It may so happen that both are exist but not equal. But there is a theorem: if all the a1, a2, an are non-negative, then, and if this s1 exists, s1 may not exist, maybe diverge, maybe infinity. If it is finite, s1 is finite, and all the ai's are non-negative, then s2 is exists and s2 equal to s1. If they're non-negative term, then this you can rearrange the term. And this type of sequence, if it is is negative term, it may be negative a1, a2, and if you consider the absolute sum, then it's called, and the sum of the absolute values. This series actually, if a1, a2, dot an is may converge, some negative terms are there, but this absolute sum may not be converged. If it is converged, we call it absolute convergent. The series is called absolutely convergent, and if the sum of the absolute number is not converged, is diverged, but the sequence is converged, then it's called conditionally convergent. In real analysis, we know this thing. In real analysis, this is called conditionally convergent, and this, if this sum of the absolute term is converged, then it's called absolutely convergent. Now in probability it is easy, and for measure there is no question of conditional convergent because all the terms are non-negative. So in this, since all the terms are non-negative, the mode of xi's are actually the ai are ai, because they are all non-negative terms. So there is no question of conditional convergence. So this issue is resolved. So this is the basic idea of Borel sigma algebra and where the measures start. And next lecture we see what is the measure and how can we construct a measure like length or area in Borel sigma algebra R, or Borel sigma algebra R2, or maybe volume in R3, or maybe more generally is a like a integral. Integral is also a measure. Integration is also a measure. How we could take a Riemann integration or some Lebesgue integration on the Borel sigma algebra. And there is some Lebesgue integration on the Lebesgue sigma algebra also, but we are not discuss on that. We discuss on the in the real analysis we discuss the Riemann integration and the Riemann-Stieltjes integration, and these are all actually major. The Riemann-Stieltjes integration, but we are confined our all thing in the Borel sigma algebra only, not in the Lebesgue sigma algebra. We just take our sigma algebra as a Borel sigma algebra everywhere for whatever it is a Lebesgue integral, or maybe Riemann integral, or maybe a Riemann-Stieltjes integral. So this is for this this lecture. So I stop now.